Okay. So yesterday, you worked on watching a video on buffers, okay? The key takeaways from yesterday's video is to know that buffers are made in two parts. You have two parts to every buffer, okay? It's only the weak acids and the weak bases that can make buffers, and they're always paired with their conjugates. So there's always two components of every buffer. Okay, but they're weak. So that means you got to know your strong acids to know your weak acids, right? 6 strong acids, so that by default any other acid other than the 6 is weak. Okay? Or they're weak bases with its conjugate. Remember, the group 1 and group 2 metals with the hydroxide are your strong bases. Anything else is weak. A lot of those carbon, hydrogen, nitrogen groups, weak bases. Okay? And a lot of times when you make a buffer, okay, this is all in the video from yesterday, but I went into more detail. A lot of times when you make a buffer, you're going to use an acidic salt or a basic salt as the conjugate. Okay? Because remember, you don't just, in my storage cabinet back there, I don't just keep ions. They're always in the form of an ionic compound, like a solid, that you're going to make ions when you put it in aqueous solution, right? So that's why we get the other part of the buffer as a salt. Okay? So we looked at the two parts in the video. Okay? I showed you yesterday that you have a weak acid and its conjugate base. Okay, here's another weak acid, conjugate base. And then here's a weak base with its conjugate acid. Okay, so those are examples of buffer solutions. Okay, interesting fact that the more moles you have, the better the buffer. So you don't want something really, really small amount of moles. You want large moles, okay? Okay, I also went into some examples where you could see what kind of buffer, how to make a buffer, okay? So I'll just do the first one with you again, just to review. All these examples are online. Okay, but if you wanted to make a buffer with hydrocyanic acid, you would need to have a conjugate base with it. Okay, so you're looking for something that's got CN -1. Okay, and that's where you would use your salt. Okay, so you could do something like lithium cyanide, right? Because the lithium is not going to count, and it's just going to give you those CN ions you need. Okay, I just picked lithium. It could have been sodium cyanide, barium cyanide, anything with group 1 or group 2. Okay, same thing with nitrous acid. Okay, if you want the conjugate base, you're looking for NO2 to the -1. So you would pair it, you could pair it with sodium nitrite, lithium nitrate, any of those group 1, group 2. That's what you could do to make the buffer. Okay, this one, it left up here. This is sulfurous acid. Okay, I just wrote the equation out to give you a buffer equation here. Okay, that's your weak acid. The conjugate base you're looking for to make would be this HSO3. Okay, so you could get sodium bisulfite. Okay, that's the base you could use. Or excuse me, the basic salt you could use to make the conjugate base, which is what you need here. Okay, so hopefully that's a little review on buffers from yesterday. Okay, we did talk about the pH of buffers, how to get the pH. Okay, each buffer solution has its very own pH. It's very, very close to the Ka value. Very, very close. Okay? I'm sorry, the pH is very close to the pKa. Remember, when you put a P in front of anything, you're basically saying it's the negative log of whatever. Okay, so the pKa, I don't know if you can see it on the screen, is the negative log of Ka, which is that constant you look up. Okay, And you're going to find, when we did our example problems yesterday, okay, so what we did was we took this acetic acid with acetate base, conjugate base. Okay, we did our ice table. These are our given quantities that they gave us in the problem. We solved for Ka. Okay, actually I looked up Ka for acetic acid. This is looked up. Actually, this is given, but looked up in the table. I just used my solver to find X. Again, you actually could cancel out the X's. I just used my solver. And I got X is 3 times 3.6 times 10 to the negative fifth, which is my hydronium concentration. Plugged it in, and I got a pH of, I think, 4.4. Okay? And if you look at the Ka, the pKa, it's pretty close to that as well. Okay, now we did the same thing. So in this case, I want to point out that I wrote the buffer with the acid first. You see that I wrote the acid first, and then the conjugate base is over there. You can write it either way. But what I would suggest, tip for living in AP chemistry, is always write the acid first. It's nice to have a way that you always do it the same way. So always write the acid first. Here's why. We did it again in our example problems, where we wrote the base first. Same exact problem. Okay, and this is all in the video if you didn't watch it. Solve for X though. Remember, for X now we're getting the POH. You also have to get the KB, which is not something you look up, so you have to do an extra step to get KB. Let me make this smaller. Okay, but when you get X now you're getting OH. Then you have to get POH. Then you have to subtract from 14 to get pH. And you see, I don't know if you can read it here, but the pH is actually 4.4. It comes out exactly the same. So I've proven to you that you can write the buffer either way. Acid first, conjugate base on the right, base first, conjugate acid on the right. My suggestion to avoid having to solve for Kb, having to solve for POH and then pH, is you write the acid first. Saves you steps, okay? How are we doing at home? Are we okay with all that? You should have watched the video and learned all that. If you need to watch it again, thanks, Quinn. Okay. Here's where I'm going to make things shorter for you. So this is all new. Okay, so if you've kind of been like not listening, this is the time to listen now. We have an equation called Henderson-Hasselbach. Okay, that actually makes it easier to solve these buffer problems without the ice table. So you don't have to use the ice table anymore. I've proven the ice table works. We can solve for it. But what you're going to do is you are going to use this equation here, which is pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. And let me just make that clear, that's the log of the whole thing, okay, not just the base. Okay? So this is what's called, now remember pKa is going to be the negative log of Ka, okay, which you look up in your table. Okay, if you have the honors table, okay, it's on the back of the polyatomic green sheet on the ions. I also posted it in the reference sheets for people at home that haven't received their reference. You can also Google it. Yesterday I was Googling some Kas because they're not always all there. Okay, so you can Google like Ka. Okay? Okay, so here it is again. Now here's a very good tip, okay? You can do it in moles, you can do it in molarity, but they both have to be, B and A both have to be in the same thing, right? Remember, if this is, let's say I had 2 moles of B and 1 mole of A, and they're both in 1 liter, right? If I put, this is B, this is A, okay? If I just use moles, I'd be putting 2/1, okay? But look, if I also used it in molarity, 2/1 over 1/2. I'm sorry, 1/1. These ones would cancel out anyway. So that's why you can do it in either moles or molarity, but they both have to be it. You can't do one in molarity and one in moles. Okay? Now, just to give you a hint, if they ask you to predict or estimate, the pH will be almost approximately pKa. So you can kind of predict. You could look up a Ka, get the pKa, and you can kind of predict what the pH should look like. This will adjust it just a little bit. I found that it adjusts it maybe by like 0.2. That seems to be what the adjustment is. Okay, so again, repeat, you can work in molarity or moles, but the B and A both have to be in each. Okay, and again, the pH of the buffer is close to the pKa, okay, which means you can have buffers of any pH. Okay, so here is an example. Okay, so take a minute to read the problem. And I'm going to get my notes out. Okay? Okay, so the question is to determine the pH of a buffer made with 0.25 molar HF and 0.75 molar sodium fluoride. Before calculating, predict what you think the pH would be by examining the exponent on the K value. Okay, so another way to estimate pH, which is good for AP, especially since you can't use calculators on the multiple choice. Does anybody know? Let's look up first. Okay, so we are going to do HF as our acid, so we're going to look up the Ka of HF. Okay, if you look up the Ka of HF, okay, depending on where you look, my green table for honors tells me it is 7.2 times 10 to the negative 4. Okay, now what I've been told to do, does anybody know how to estimate the pKa from this number without using a calculator? Do you know how to estimate it, Chase? Yeah, I think I usually just estimate, I take the absolute value of this number here. Okay, so that's going to be 4, and then I usually subtract 1. So my estimate for my pH would be 3. Okay, so that would be my estimate of my pH. Okay, without using a calculator. Now, if I actually take the negative log of this number, I get, which I can use in my equation, I get 3.14. Okay, but it's good to be able to estimate something that you have to take the log of when you don't have your calculator, okay? Because remember that multiple choice in AP is no calculator. Okay, and honestly, I did not know. I knew it when it was like 10, but I didn't know how to do it when it was like anything else, to tell you the truth. So I just learned that myself. Okay, so now what we're going to do is calculate it using Henderson-Hasselbach, okay? So our Henderson-Hasselbach equation is pH equals pKa plus the log of B, concentration of B, which is your base, over A. Okay, now I already told you that I calculated the negative log of 7.2, which was our Ka, 7.2 times 10 to the negative 4th. So I can plug that right in my pKa. It's 3.14. I'm sorry. Yeah, that's right. I'm sorry. Yep. 3.14 plus the log Okay, now remember the B is the base. In this case, the base is going to be your NaF. It's going to be the F negative 1. So that's going to be the 0.75. Okay, and the acid is going to be the 0.25. Okay, so that goes on the bottom. Let me just pause this for a second. Okay, so we got 3.14, which is the pKa, the negative log of the Ka, which we looked up, plus the log of 0.75 over 0.25. Notice they're both in molarity, so it's cool. Okay, equals, I get a 3.61. So I actually think, I'm not sure about this subtracting one. I have to look up that thing. I'm not sure if you just take the absolute value of the exponent or subtract one. I'll have to look that up. 3.61 is your answer for pH. Okay, so that's how you do that. I'll give you a minute to write it down. Take a break for a second just to absorb what we just did, and then we'll move on. Okay, just to correct, for the estimating of the log thing, let me just show you what they say, you know, on the internet about doing this, just to be clear. They actually say to take the exponent, okay, and take the absolute value, which is what we did. And then it says to subtract, okay, you take the number there and basically divide by 10, so you're going to make it 0.72. Okay, which is about what, 3.3? Something like that. Okay, so if I wrote out a formula for it, let me see if I can just put in a new slide for this. Let me know if I write this wrong, Jake, but I think I got this. Let's see. So if you have a log of m times 10 to the negative n, and you want to estimate the answer without your calculator, what you're going to do is take the absolute value of your exponent and subtract 0.m. And that's going to give you an estimate without your calculator. So if you want to write that down, that's a good tip for any multiple choice when we do the AP without a calculator. Has everybody got that written down, or thumbs up, thumbs down? You guys laying down? Quinn, do you understand? Okay, so let's go on to the next example. Okay, here's the next example. Determine the pH of a buffer made with 0.5 molar NH3 and 0.2 molar ammonium chloride. Before calculating, predict what you think the pH will be by examining the exponent on the K value. Okay, so do a little prediction, and I want you to put it in the chat. You guys want to just shout it out what you think the prediction is. I'll look up the Ka for you first, and I'll put the Ka value up. So keep in mind, guys, I am going to write acid first, so I'm going to look at the Ka of the acid. The acid is going to be the ammonium ion, is what I'm looking at the Ka value of. Okay, so the Ka of this ammonium ion is 7.2 times 10 to the negative 4. Oh, wait, I'm on the wrong one. Hold on, let me switch. I didn't switch my page. Excuse me. It is 5.6 times 10 to the negative 10th. I'm reading the old one. 5.6 times 10 to the negative 10th is the Ka value. Okay, so I want you to predict what you get. Okay, so I want to see your predictions in chat. Okay, let's do this. Make sure you understand. So remember, we're taking the absolute value. Okay, so it's going to be the absolute value of 10, okay, which is minus 0.56. Okay, we can just estimate 0.6. So it's going to be 10 minus 0.6, which should be about 9.4. That's our estimate. Okay, that's our estimate because it's pretty close to the pKa. Okay, good, good, good. All right, now, this would be like the top one. I think it's,
yeah.
it's on there?
There's a PK and then the opposite PK.
Okay. That's it. This is it. Just like a little bit different. Okay, great. Yeah. Okay. Yeah, so Henderson Hasselbach is on the AP Chem equation sheet, okay? All right, so let's go through the problem. So we have pH equals the negative pKa, or not the negative pKa, just the pKa, which is 9.3, which I actually calculated. So the pKa was 9.3. Plus the log, okay, remember it's the base over acid. The base was 0.5. The acid is 0.2. And I get an answer of 9.7. Okay, I ended up using 2 sig figs just because most of the, it had 2 sig figs in the given. Okay, so you should have got 9.7. Okay? Any questions about that? Okay, so this is another type of problem. Okay, determine the pH of a buffer made with 1.60 moles of LiOI and 1 mole of HOI. Before calculating, predict what you think the pH will be by examining the exponent on the Ka value. Okay, so let's pause the video. You do this yourself. Okay, first put in your prediction and then solve for pH. And then we'll solve together. Okay, let's do this together. 2 times 10 to the negative 11. Okay, so the first thing is to look at the Ka of HOI. 2 times 10 to the negative 11. These OI ones are not on the honors reference sheet, so I end up Googling them. A lot of the OCL ones, anything with this like O, I don't have them on my reference sheet, so I end up Googling them. Okay? So the Ka is 2 times 10 to the negative 11. Okay, so if you're going to estimate what the pH is by the pKa, which we're going to estimate, you're going to take that 11, right, because you're going to take the absolute value, subtract 0.2, and you should get about 10.8 as your estimated value for pH. Okay, then using Henderson Hasselbach, okay, pH, again this equation is on your reference sheet, is going to be the pKa plus the log of the base over the acid. Okay, so let's make sure we know which one's the base and which one's the acid. Okay, and then in the video yesterday, remember I proved that it didn't matter which way you wrote the equation. Okay, but for the Henderson Hasselbach, it's It's got to be base over acid. Okay, so this is our acid right here. That's our A, which is our 1 mole. Oh, let me write it on the bottom. Okay, and then our B is going to be our OI, -1. So this will be our V, which is 1.6 moles. And notice you can use moles, because they're both in moles. If they were over liters, the liters would cancel out anyway. Okay, the pKa, I believe I got 10.5 for the pKa when I actually solved it in my calculator, plus the log of this beauty over here, and I ended up with 10.7. Okay, now again, remember I Google different numbers and stuff sometimes, so it could be just a rounding. As long as you're very close to that, I think you're good. Okay. I never looked, when I got this 10.5 here, I never looked up I just looked up pKa. Okay, so this may be where some of the numbers are a little off, okay? All right, so it looks like you're good. So you're going to be practicing a lot of those types. I think I forgot to press record. Okay, so this is how you solve the ratio if you need B over A. Okay, you use Henderson Hasselbach, plug in. Okay, then 10 to the negative 0.18 equals B over A, which is 0.66. Okay, so this is just when you need to get the X, and it's in the log, this is the formula you would use to get the X by itself. Okay, and that's the one we use when we solve for concentration, when we're given the pH of like a strong acid or a strong base as well. Okay, last problem is a thinker. I'm going to let you guys work on it on your own and then get the answers, and then you guys are on your own to work on the sheet. We got plenty. Do we have plenty of time? A little bit of time? Let's see. Okay, so let me put this problem up. Pause the screen. Okay, so just in general, pH does not equal pKa if it's a general acid-base solution. The only time it's close is for a buffer because of the common ion effect. Okay, so pKa is only approximately, pKa is close to pH only for buffers. Okay, now, here's a thinker problem. If you want a buffer with a pH of 3.75, what chemicals would you choose? Could you figure that out? Okay, if you want a buffer with a pH of 8.6, what chemicals would you choose? All right, let's do the first one together, and then I'll let you do the second one on your own. Okay, so what I did was I said, okay, well, I have a pH of 3.75. Okay, that's going to be, I'm going to assume that 3.75 is also going to be approximately my pKa, right? Okay, and then I solved for my Ka. I basically said, well, Ka then will be 10 to the negative 3.75. Okay, which I got a Ka of about, I kind of rounded just to, I got 2 times 10 to the negative 4. Okay, so that's the Ka. So what I wanted to do was look up 2 times 10 to the negative 4 to see what that would look like. What acid conjugate base that would look like. And when I looked up, the closest one I found on the tables I was looking at was nitrous acid. Okay, so I thought the buffer pair I could use would be my nitrous acid And then I just put together a salt with a conjugate base. So I said, okay, well, I could use lithium nitrite. Okay, because that's where I could get my base. Okay, so again, just to repeat, what I used was, I said this was approximately my pKa, got my Ka, rounded it a little bit, looked it up on my table or Googled what was close to 2 times 10 to the negative 4, and from my green table, I got nitrous was the closest. Nitrous, and then my conjugate base I would get from my basic salt. Okay, so see what you could do with the next one on your own. Again, I used my reference sheet. Okay, so what chemicals would you do? All right, so I wanted a buffer of 8.6. Okay, so I said this is approximately my pKa. Okay, and then if I want my Ka, I'm going to take 10 to the negative 8.6. Okay. And then I think you can actually just estimate this again, just take the absolute value. So you're looking for something, or no, I guess you don't take the absolute value. You're looking for something around that exponent, -9. Okay, if you take the actual Ka, I ended up with 2.5 times 10 to the negative 9. I think you're really just kind of looking for that exponent. Okay, so I ended up getting phenolphthalein when I looked it up in the honors table. I'm sure there's more correct answers, which would be the HPHTH is the acid, and then the base would be basically any group 1 or group 2 to make the salt. Okay? Other answers are possible. I just don't have the chart in front of me. All right, so I am done.